Okay, good afternoon, everybody. So today's lecture is a continuation of the previous lecture where we were looking at pathing. So just to quickly remind you what was going on before, we looked at two different algorithms in the last class, right? So we looked at Dijkstra's algorithm, and we looked at greedy best first search, right? So remember, Dijkstra's algorithm is guaranteed to find a shortest path from a start position to one or more goal positions. The way Dijkstra's algorithm works is that it can find the shortest path, but it often does more work than it needs to find the shortest path. Right? If you stop and look at the implementation of Dijkstra's algorithm, you'll see that Dijkstra's algorithm favors grid locations that are closer to the starting point. Right? So you start at the starting point, and then it explores around the starting point. And then it basically repeats the process, and it always tries to it always expands the search at points that are closer to the starting point than further away. And that's why it ends up doing more work than it has to in most cases, right? Whereas greedy best first search, it's not guaranteed to find the shortest path between 2 points, but it usually does so. It usually does less work to find a path than Dijkstra's algorithm will perform to find the shortest path. And that's because greedy best first search always tries to move towards the goal location, right? And so sorry, that doesn't work. Anybody here use a Mac? How do you get your cursor to show up on the screen when you're presenting? Anybody know? Anybody actually know? I don't normally use a Mac. Okay, so anyway, on the right here. So here, to get from here to here, greedy best first search tries to search in the direction towards the goal. And so it's here you can see it takes this path to go into the concave shape here before it figures out it has to go around. Right, Dijkstra's algorithm figures out it has to go around, but it has to search everything that's shaded in order to do so. Right, so the shaded squares here are the squares that are actually evaluated for their cost. Even though the path that's computed by greedy best first search is not as good as A star, it still does a lot. It still does. In this case, quite about half the amount of work that Dijkstra's algorithm has to do. Okay, so for Dijkstra's algorithm, there is it simply expands the search, starting at the points closest to the goal. Greedy best first search uses a heuristic function, right? And so remember, it's always looking at a point that's closer to the goal location, right? The closer to the goal location is obtained using this heuristic function. So here, remember, greedy best first search uses the function called h of n. So that's just the estimated cost of getting from node n. So node n here is grid location n to the goal node. And so A star uses the heuristic function, and it also uses the cost so far function, G of n. So that's the function that Dijkstra's algorithm uses, right? It takes the number of steps to the current location, right? And it expands the search around the location that has the smallest G of n. Right. Greedy best first search chooses the grid location with the smallest H of n. A star combines both together into one. Right, and so A star expands the search around the grid location where G of n plus H of n is the smallest. Remember, G of n and H of n for a grid, it's just the distance between the location to the start point for G of n. And for our purposes, H of n is just the distance from the current location to the goal location. Right, and the distance is normally measured as the Manhattan distance or city block distance. Right. So it turns out A star is guaranteed to find the shortest path if you pick an appropriate H of n. Right. So I'll have more to say about H of n shortly. So this is what A star does when given a goal and search location. Right. So if that's the goal sorry, that's the start, that's the goal, that's the goal, the start, that's the goal. If there's no obstructions between the goal and the start location, then depending on how you've implemented A star, you can get A star to search more or less only in the direction of the shortest path. Right, so here it searches in the direction of the shortest path plus one square around the shortest path. Here we've got the same example as before, where there's this concave obstacle. And here you can see that A star has done less work than both greedy best first search and Dijkstra's algorithm, yet it produces the same path that Dijkstra's algorithm produces. Right? It only needs to evaluate the shaded squares to find the shortest path to the goal location in this case. Right, so it looks like A star is what you'd normally want to use if speed of computation is a consideration. Okay, so what does A star do? So it's basically the same as greedy best first search and Dijkstra's algorithm. It's just that instead of using just G of n or H of n, it uses the sum of the two. So we've got our start location in green, we've got our goal location in orange. Right, so starting at the start location, you're going to search around the start location, evaluating these two functions, G of n and H of n. So G of n is the first number, and H of n is the second number. G of n is just the distance to the start location. So that's one square away from the start, that's one square away, that's one square away, that's one square away. The second number is the distance to the goal. Right? So that is 1, 2, 3, 4, 5, 6, 7, 8, 9 steps to the goal. Right? That's 7, that's 7, that's 9. Sum up the two numbers, you get 10, 10, 8, and 8. Right? And so that's the first iteration of the algorithm. Right? All of these cells or grid locations that you just visited, you put those into a priority queue. And the next iteration, you take out the smallest, you take out the grid location with the smallest value in the priority queue. So you're going to take out one of the two 8s. So next step, right? So let's say we take out the 8 from here. You repeat the process. You look at its unvisited neighbors, right? And so that's an unvisited neighbor. What's the cost to reach that square from here? Well, it's 1, 2. What's the cost from this square to the goal? Well, it's 1, 2, 3, 4, 5, 6, 7, 8. Right, so you're 2, 8. So that's total of 10. Right, you do the same thing with that square and that square there. Right, and now you've got 10, 8, and 8. Right. That 8 is still sitting in your priority queue. Depending on how you've implemented your queue, it's the oldest element in the queue, so you pull it out first. Right. The choice here is, do I expand here, here, or here at this step? Right. The way that Dr. Graham has drawn the slide feels like expand the oldest one. So now you expand this one, right? The distance G of n to this square is 1, 2, and H of n to this square is 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, yeah, 6. So 6. Right, and now you've got an 8, an 8, an 8, a 10, a 10, a 10, and a 10 sitting inside your priority queue. Right. Next step, you're going to pull out one of the 8s. Right, and in this case, it turns out when you work out the algorithm, you end up pulling them all out eventually. Okay. So pull out that one. Right, the distance to that square from the start, 1, 2, 3. The distance from that square to the goal, 1, 2, 3, 4, 5, 6, 7. So you get the 10 up there. Right. Same exercise here. You get 3, 5, 3, 5, 3, 5, 3, 5. And now you've got 8, 8, 8 sitting in your priority queue. Right. So you got your 8s. You got your 10, your 10, your 10, your 10, your 10, and your 10 sitting there. Right, next round, pull out the smallest values again. So starting at that 8 there, process. Right. Look at its neighbor. How far is it from the goal? From the start? 1, 2, 3, 4. How far is it from the goal? 1, 2, 3, 4, 5, 6. So there's 10 there. Right. Repeat the process, and you get all these 4s. All these 8s. The 10 is there, and a new 10 is there. And if you keep on going, right? You eventually end up running into the goal location, at which point you can stop. And so A star here, if you compare this to the Dijkstra's algorithm, it's basically done the same amount of work in this case. And so the simple version of A star, at least in this case, does the same amount of work that Dijkstra's algorithm does. A little bit earlier, I showed you that if you have no obstruction between the start and goal, it's possible to get this to work out to only evaluate locations from the start to the goal. Right. In other words, we can hopefully avoid calculating all of this stuff up here. And there is a way to do that. Right. Once you've worked out that you've reached the goal location, you can now work backwards and find a path back to the starting location. Right. The path is not unique. Right. So there's many paths that all have the same cost for this particular problem. Right. You can go from here to here. You can go from here to here, and so on and so on. Right. So there's many different ways to choose a path with the same cost. Okay. Any questions so far about how this works? Right. So how does this work when you've got something in the way? Right. So if something's in the way, so the black boy, right? For its heuristic cost, you just evaluate the cost to be infinity. Right. So when you hit this square here, you say, how far does it take? What is the cost to reach the goal from here? And you say it's infinite, right? It's infinite, so you can't cross this square. So you do the same thing. That me? That was weird. Oh, was it?
Yeah.
Fun. I don't know what that was all about. All right. Oh, this must have been oh, I see. It's because he's got it labeled as exercise. So I guess he meant for you to sit here and work out exactly what's going on. Right. Rather than have you work out what's going on, let's just do it on in the lecture itself. I guess that's what I was wondering what that was. There's a file called jeopardy.something. So I guess that's what the sound file was. Okay. So you start out at the goal. Right. So we know that g of n for the goal is 0, right? How far is you start out at the start, right? G of n for the start location is 0, right? The distance between the start and the start is 0. The distance to the goal is 8. Right? When you compute the distance to the goal, you never consider what's in the map. You never consider any obstructions in the map, right? Why it's called a heuristic, right? It's a guess at how far it is. So how far is that from here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you pull the starting node out of your queue, you evaluate all of its neighbors. So the distance to all of its neighbors is 1, which is why from the start to the neighbor is 1. Right? And then you calculate the distance from each square to the goal. Right? 1, 2, 3, 4, 5, 6, 7, obviously 9 and 9. Right. So you now got a 10, an 8, and an 8 sitting in your queue, right? Or nodes with 10, 10, 8, and 8. Right? Pull out one of the 8s. Right. So we get 2, 8, 2, 6, 2, 6, 2, 8, and infinity 2. Infinity 2. This should be 2 infinity. You got that? That's written backwards. But 2 infinity. Right. So for the 1, 7, right? G of n is 1, 2. So that's what the 2 comes from. The 6 comes from 1, 2, 3, 4, 5, 6. Right. So you've now got a 10, an 8, an 8, an 8, and a 10 sitting in your queue. Or nodes with 8, 10. 10, 8, 8, 8. No, you expanded that node, 10, sitting in your queue. And so those are the potential next nodes. Right. So we've got a bunch of 8s. So pick one of the 8s and evaluate it. So I guess Dr. Graham's evaluated that one. So G of n is 3, H of n is 5 for that one, 3, 5, 3, 7. Okay. And you've now got the 10, an 8, and a 10 left in your queue. right? Pick out the smallest one. So that's going to be the one with the total cost of 8 and evaluate it. Again, these are all backwards. So when you evaluate 3, 5, right? The cost from the start to that location is 4. The cost from that location to there is 6 to get to 10. Right? And now you've got a 10, a 10, a 10, a 10, a 10, and a 10 sitting in queues. Okay, so expand the 10s and you get that. Right. Eventually, you're going to expand the bottom 10. And it you get 4, 6. Right. And now you keep on going. Right. So expand the 4, 6, you get 5, 5, and 5, 7. Right. Then 6, 4, and 6, 6. And obviously now you can see that it's going to work its way to the goal. Right. And to get 10, 0 there. Right. And so there's how the simplest version of A star works its way around an obstacle like this. Right. If you stop and think about what Dijkstra's algorithm would do, right? Dijkstra's algorithm works its way out from the start, right? So it would have evaluated all of those locations as well, right? And probably some down here as well. Greedy best first search would have done something like try to move in this direction and then. Okay. So the key in A star is this heuristic function, right? So if you stop and analyze the 3 different methods or 3 different algorithms for pathfinding, right, and you play around with H of n, you'll quickly realize a few things. Right? So if you pick H of n to be always equal to 0, in other words, always ignore the heuristic cost, then you just end up with Dijkstra's algorithm. Okay. Similarly, if your H of n is always much bigger than G of n, then you just end up with greedy best first search. Right? So in other words, Dijkstra's algorithm only uses G of n, greedy best first search only uses H of n. Right? Everywhere in between, there's a gradient of what happens. So if H of n is always less than the true cost of moving from the node n to the goal, A star is guaranteed to find the shortest path. Right? At the cost of potentially evaluating more grid locations. Right? So remember what H of n is. H of n, you're trying to estimate the cost of moving from n to the goal. Right? So if H of n underestimates it, we say that H of n either underestimates it or gets the true value. We say that H of n is an admissible heuristic function. Right? And so if you read the A star literature, you'll see a lot of talk about people saying, often people will say you should always use an admissible heuristic. If you can somehow arrange for the fact to get H of n to be equal to the true cost of moving from n to the goal, then A star is guaranteed to evaluate the shortest path. It will produce the shortest path. Right? And so in general, you can't do this. Right? The only way that you can get this in general to be true is if you compute the true cost ahead of time. Right? So in other words, if you pre-process one way to do it would be to pre-process your map with Dijkstra's algorithm, right? And then store it somewhere. Right? If you can afford to do that, then you can get A star to always produce. I'll give you back the shortest path. Okay, so remember again what H of n is. It's an estimate of the cost of moving from n to the goal. So if you overestimate the cost, right, then A star is not guaranteed to find the shortest path, but it might find a path in less time. Right? So in other words, it might evaluate fewer grid locations. It'll give you back a suboptimal path, but that's okay. That might be okay depending on what you're trying to do. So if H of n is greater than the true cost, then we say that it is a non-admissible function, right? Not guaranteed to find the shortest path. So in most cases, so especially games, where whether or not you find the shortest path is actually critical, is probably not critical, right? You can play around with H of n to balance the trade-off between speed and accuracy, right? So speed, evaluate fewer locations than you have to. Accuracy, you might produce a longer path. right? And so often in games, you don't need the shortest path. You just want a path. Hopefully a path that's not too bad, right? Doesn't wander all over the place. Right. So usually a good path is all that's required. You don't actually require the shortest path. So what that means is that when you're using a star, you can consider a non-admissible heuristic to improve the speed. Right. So in other words, it might be better to choose the heuristic that overestimates the cost of the goal. Right. In other words, make it behave more like 3D best first search. Right. So there is the first instance of this is the using A star, a simple implementation of A star. Right. So this uses the Manhattan distance. The Manhattan distance turns out to be an admissible heuristic function. Right. It never overestimates the cost to the goal. Right. So what happens if we plug in that instead? So instead of using just the Manhattan distance, why don't we use 1.01 times the Manhattan distance? So in other words, take the Manhattan distance and multiply it by 1 and add 1%. Right now, what happens to the path and sound? Right, and it turns out you end up getting a path that might look like this. You won't necessarily get this exact path. It depends on how the details of how your algorithm is implemented. Right, but if you just make this small change here, you end up not evaluating all of this stuff here. Right, but now you only evaluate the squares around a shortest path to the goal. Right. So the yellow is a shortest path, and you only evaluate the squares on the shortest path and the median and one around it. Right. And so you say, well, that's kind of cool. How did that happen? Right? How did I go from here to here just because I multiplied the Manhattan distance by 1? So the answer is you just draw it out. So we start at the starting location. We look at its 4 cells around it. Right. So my G of n is always 1. Right. So G of n, I'm always taking one step to one of the neighbors. Now, what's the Manhattan distance from here to here? Right. Well, it's 7. Right. So 7 times 1.01 is 7.07. So here you get 8.07. Right. Same thing up here. Right. Up here, it's 1 plus 9.09. So 10.09 and 10.09. So you look at that grid location gets inserted into your priority queue with that cost. That one gets inserted into the queue with that cost, and those two get inserted with that cost. Right now, next round of the algorithm, take out one of the grid locations with the smallest cost. So let's pick up this one. Right, and now evaluate its neighbors. So I want to look at that neighbor, and that neighbor, and that neighbor. Okay. So G of n is 1, 2. Right. The distance from here to here is 807. Am I doing this right? Oh, sorry, here. So the distance from here to here is 1. So the distance from here to here is 2. The distance from here to here is 2. The distance from here to here is 2. Okay. The heuristic cost of this is 6 times 1.01. So that becomes 8.08. That's 2 and 6. Am I doing this right? 8. Sorry, 6. And that becomes 2 plus 606. So it's 806. This one becomes 2 and 808. So 1008. Okay. Repeat the process. Am I doing this right? I'm doing this right? Yeah. Right. So repeat the process. I've got 2 of these 8.06s in here. Right. Pluck out one of them. right? So if you pluck out this one, right, you're now going to evaluate that and that. Notice what's happened here, right? So before, we have an, make sure I got this right. You had an 8 and an 8 here, right? Now you've got an 807 and an 806. So you're never going to expand this one until you expand one of these two, right? When you do the same thing here, over here, right? 1, 2, 3 here, right? So we get 3 and 7. So 3 and 7.07, so 1007. We're going to get 3 and 5, so 3.5, 8.05. And we're going to get 8.05 here, right? Again, notice what's happened, right? Before, we had 888 here. Now you've got 807, 806, and 805 here. So you're going to expand this before you expand this, before you expand this, right? And so simply by paying this little trick of multiplying the Manhattan distance by a value greater than 1, you end up producing a path that might look like this, right? It might not look exactly like that, so it can wiggle, right? So if we, instead of evaluating this square first, you might have evaluated this square first. Well, that's fine, it's just going to do the same thing, right? But here it's going to turn, and it's still going to find the shortest path, right? That function there is not necessarily admissible, right? So in other words, it might overestimate, it definitely overestimates the cost in this case, right? But by using a non-admissible function, we greatly reduce the amount of work that it needs to do to find a path, right? And in this case, it also finds the shortest path. All right, any questions about what's going on there? Right, so really what's happening here is that you're breaking the ties that used to exist. Or we had lots of elements, lots of nodes that had an 8 in them, right? Here you don't have that case anymore. The closer you get to the goal, the smaller the value of f of n gets as you get, the smaller the value of f of n gets. Right. So rather than expanding that one, you're always going to expand nodes closer to the goal. Right. So scaling h of n by a small amount has the effect of breaking ties in our total cost function f of n. Right. And it turns out there's a bunch of ways that you can break ties. Right. And so scaling the heuristic function isn't the only way to do it. Right. A different way that you can break ties is that in your priority queue, you always give newer insertions higher priority than older insertions for the same value of the priority, right? And so if you do that in this example here, you don't scale the values, right? What ends up happening is, so if we don't scale, but we always treat the, we always put them, we always put newer in, we always weight higher insertions higher than newer insertions. As soon as you expand this one, right, you'll get an 8, I think an 8, right? I think it's always 8. Yeah. You get an 8, you'll get an 8, and you'll get an 8. Right, but that 8 will have a higher priority than that one. This one will have a higher priority. Well, depending which order you insert them in. These ones will have a higher priority than that old 8 there, right? Because you insert these ones. Or you inserted these ones more recently than that one there. Right, so it turns out that also works, right? And yet another strategy is to add a small cost to the penalty if the direction of your path starts to change. That's a bit vague, so I have to draw this out for you. What you have to remember in Dijkstra's algorithm and in all of these algorithms is that you always remember, or you're keeping track of how you reach the node, right? So suppose we start here, right? And we move to this node here, right? So part of the information that you store is how you reached this node, right? So if I now expand around this node and I decide I want to change direction, right? So here I'm going horizontally and now I'm going to go vertically, right? You can impose a smaller extra cost to changing directions here, right? So in other words, the cost here So I'll call this F1 of n. I'll call this one F2 of n. So F1 of n is going to be slightly greater than F2 of n here, right? Because the path changed direction here. And so if you use this strategy here, you're going to bias the algorithm towards always moving in the same direction, right? But that also works to avoid this changing. This also works to break ties. Okay, so that's those are all simple cases where you've got one type of terrain or one type of one type of terrain, I guess is the best way to put it, right? You have one type of terrain, you might have some obstacles in the way, right? When I showed you Dijkstra's algorithm, right, I explained that, hey, Dijkstra's algorithm can also handle different types of terrain, right? So rather than the cost of moving one square being one, what happens if g of n changes, right? So for example, here, I've got some very badly drawn mountains, right? So if you assume that the cost of crossing the mountain is much smaller than the cost of walking around, I guess, in the white area, right? What does A star or even the greedy algorithm, what do they do? Right? So if we assume that the cost of moving into a mountain location is 5, right? Then what does A star do? Right? So your g of n becomes 5 when you try to step onto a square that's up. So here, going up one more costs me 5 extra. Costs 5 extra whatever, right? Whereas if I went this way, g of n only costs 1 more. So here would be 1, 2, 3, 4. Then move this would be 9. Right? 1, 2, 3, 4. Then move here would be 1. So that's 5 versus 9, right? And so A star is going to want to go around the mountain rather than trying to cross the mountain, even though this path here is really shorter. Right? If you actually calculate the total cost. Right? So in other words, this thing is going to explore the path out this way before realizing, oh, I could have gone across here to get to the goal here. Right? And so the trick here is you widen A star. Right? So you can artificially increase the cost of moving in the white area in order to bias A star to consider the mountain locations earlier. Right? So rather than telling A star, hey, the cost to move from here to here is 1, you can say it's 1.5. Right? And so that way, when it reaches here, it's going to search a shorter distance this way before it realizes it can step into the mountain, pay the cost of 5, and then cross the mountain and realize crossing the mountain is better than walking all the way around. Right? And so you don't have to, you can lie to A star, right? You just have to manipulate g of n and h of n, and you can change the way it behaves. Okay, so once you've got your path, now what do? Right? So you're going to use pathfinding to establish a high-level route with respect to your underlying grid. Right? So if I want to move from the start location to the goal location, I need to follow that path there. Right? Now, what you have to remember is that your grid locations might be very large. Right? So this grid could be very coarse. And so what you need to do to your AI controlled agent is you need to move it from here to here. Right? So how do you do that? Well, you just use a steering algorithm. In other words, you say each grid location is a waypoint, and now you move from waypoint to waypoint to waypoint. Right? If there's other agents moving in the world, right, your steering algorithm hopefully has a collision avoidance algorithm as part of it, so it will move it around any local obstacles here, right, to get to that waypoint there, and then you just repeat the process until you get to the goal. Right? So pathing works at a higher level than steering. And pathing itself can also be hierarchical, right? So in other words, you can use a very coarse grid to quickly establish a path, right? And then you can use a finer coarse grid to work out how do I move between locations on the coarser grid. Okay. So for example, if this is my coarse grid, right, then from moving from here to here, I can now compute a path on a finer grid, which is the one shown in that pale color. Right? And so you can have hierarchies of maps, right? very coarse one to do quick pathfinding, a finer one to do better pathfinding between points on the grid, and so on and so on and so on, right? You might have several layers of grids. Eventually, you end up falling back to steering, right? So no matter what you do, you basically end up moving from waypoint to waypoint. Sorry, I just want to check the time. Okay. Okay, if you want to encode information about the terrain, there's lots and lots and lots of ways to do it, right? And so I think Unity uses layers. So it uses layers to encode the different costs for moving across different terrain, right? This is basically the same idea. Here you can store a another map that encodes how hard the terrain is to move on, right? And so here, Dr. Graham is using values between 0 and 1 to indicate how hard is it to move on this terrain, right? 0 is infinitely hard, so you have an impassable barrier. 1 is easy, right? So cost of 1 to move from point to point. Right? So this would be another way to do it, right? You store the difficulty as part of your map. Okay, so we've got a slide here called pragmatics, right? So if you have a large number of things that you're trying to path, that's generally too slow to compute, right? The pathing algorithms aren't cheap to compute, right? So if necessary, you can configure all of the algorithms we talked about to return partial paths, right? So you don't have to compute a full path, right? You can compute a path from the start location part way to the goal location, right? So in other words, you can run your pathing algorithm for a fixed amount of time or for a fixed number of iterations, however you want to do it, right? You return the path that's computed up to that point, right? You move to whatever the end point of that path is, and then repeat the process again from the new starting location. So in Unity, Unity uses this thing called a nav mesh to specify the walkable parts of a map. Right. So here you can see we've got this. It looks like you've got some sort of scene set up, right? And on that scene, you can see there are these very large triangles. Right. So the very large triangles is what Unity calls a navigation map, or a nav mesh, or a navigation mesh. Right. That nav mesh is basically the graph that it's using to compute in order to compute paths on that on your map. Right. So Unity by default doesn't use a grid. It uses a tessellated. I think it's always triangle. It's either triangle or quadrilateral as its map. So both Dijkstra's algorithm, all of the three algorithms, you can reconfigure them to work on general graphs rather than on grids. Right. It uses layers for terrain. Right? So you specify as many layers as you want as part of your map. Right. Each layer of the map stores the cost for moving in that particular area of the mesh. Right. And then things moving around in this world, they use that mesh to perform pathfinding. And if you look at the Unity's documentation, it says it's actually using A star underneath. But I don't think you can tweak how its A star algorithm works. So if you want a tweakable version of A star where you can specify cost functions, so your G of n, your H of n, you have to either implement your own A star algorithm or you have to purchase an add-on. Right. And it turns out there's one add-on for Unity that implements A star and pathfinding that everybody uses. I can't remember the name of it. But for a few dollars, you can buy an A star implementation to do pathfinding in Unity. All right, so that wraps up today's lecture. I think in the next lecture, we're going to look at modern variations or modern extensions to A star so that you can, instead of moving from grid location to grid location, you can actually walk in any direction. So that'll be on Thursday.
I tried doing this in like a 2